So hello everyone, thank you for coming for the first seminar of the year. Today we have Carlos Peña Garay and Alicia Gomez is going to present his for us. So thank you for coming and welcome.
So hi everybody. So it's a pleasure for me to introduce to Carlos Peña. He holds a permanent position in CSIC, but now is on leave for being the director of Laboratorio Subterráneo de Canfranc. I think that he's one of the most intelligent persons that I know. This is not in your introduction, but I don't care. He makes his PhD on theoretical physics in Valencia, and now he went to Princeton, and now he went back and has been the director for how long? 7 years or 8 years now. He has there moved a lot of new things and new research lines. He is moving a lot the hypercande experiments in Japan. He's also supporting us a lot with a new experiments for the search of dark matter that is called CADEX, and that is one thing that is very interesting for the Center for Astrobiology. Has opened a new research line for trying to figure out how the radiation affects biological systems. So, Carlos, please.
So, good morning, everybody. First of all, thank you for joining. I will tell you a few stories. And the first one is I have lots of curiosity. I think it's why we are here and what we share. And my curiosity just brings me to at least ask myself some questions, which I have no idea about. But at least that brings me outside this comfort zone, which is what I know how to do, which is solving differential equations. That's the only thing I know. All the other is just I speculate. And thankfully, there are lots of experts around, very nice people, and try to communicate and get some help from them. And from that curiosity, and there's also insistence, I'm really very persistent and insistent. I dedicate a significant amount of time of making sure that some things happen. So yeah, we are building some stories. So my goal, or my 3 goals, is that unfortunately, underground labs are still very little known, and particularly the one that we have in Spain, 1 out of 10 in the world. So I will spend about 5 transparencies, 5 slides to at least present something about Laboratorio Subterráneo de Canfranc. So for the ones that are in biology, is just what is the context. Why at some point someone figured it out to do biology experiments in that is just what is the decades of expertise that we have in understanding better what is and how we control or understand the low background radiation. Then I will show some results in biology, not done by me or by the groups in Canfranc, by the groups that we host. And then the third is my proposal here. Is bold and a bit crazy, but little and little is becoming more realistic in the sense that potentially needed for the future of the science in trying to understand better what happens to life outside the surface of the Earth. So, and this means 5 transparencies, but that's 5 plus 5. This is 15. I have 45 minutes. And then I will save some time just with a first story. I also love stories of science. Science is full of very interesting lessons that unfortunately, most of them we skip or forget because only we just learn what was successful. And it's very important to understand also how many times we fail. This is the first, at least as far as I know, underground lab in history used for science. It was a train tunnel. This is in Scotland. And it was used by Wilson. And for the ones that know a little bit of history, Wilson was the inventor and it's a Nobel Prize for inventing the cloud chamber. And I'm sure that you saw some cloud chamber, right? So that means it's just you use the change of phase. You put some system very, very in the change of phase, and then just the passage of a charged particle with so little energy is able to change phase, and then you see it by bubbles or, okay? So this was invented by Wilson 1911 or so, or something like that, so it's more than 100 years ago. And he used his bubble chamber for some experiments. The question at that time, and that's the other thing, is which are the important questions? The question at that time is that already radiation was at the very beginning, It was discovered in the late 19th century. So and with his cloud chamber, he tried to answer one fundamental question at that time: is where is coming the radiation from? From below or from above? That was not known at that time. So, and then he designed a very easy and beautiful experiment. He took just his cloud chamber, bringing it inside some tunnel, and therefore you are kind of putting some isolation to the outside. And if the radiation increases, is that it's coming from below. For most people don't know this story. He got more signal, so that means his initial interpretation is there is more radiation coming from below, which is partially right, partially wrong. But the right solution we all know, and is by Victor Hess, putting some of these detectors, another type, but also a radiation detector. You go in a balloon, so you go high to the atmosphere, and you get more radiation. So you know that it comes from above. The real answer is that Victor Hess got the Nobel Prize because he's made these fantastic discoveries. We have lots of things coming from the sky, which are not related directly to our atmosphere. Our atmosphere makes things, but it comes from above. But these men also discovered something. There is more radiation than the one coming from above. In the tunnel, there was lots of radon. At that time, still radon was not very well understood. It's the beginning of radioactivity. And radon, in fact, was already approved by the International whatever association. We all have also these organizations just that set the stamp in 1920s. So it was not clearly understood. So there was more radon underground, and that's why he got more radiation. So that means the lesson is there are other sources of radiation. But the answer to the question was the one by Victor Hess. So this is formally, as far as I know, the first underground lab used for science. It's just a train tunnel. They have to work when there was no train. So it was in use at that time. So that's the story for today. Now let me just discuss that what happens for more than 100 years. And we have a few labs in the world. The largest one is in Italy. It's named Laboratorio Nazionale del Gran Sasso. This is the largest one instrumented. In fact, last year was started the new largest one that is in China, but it's mostly empty. So for the moment, I still keep Gran Sasso as the largest instrumented. The deepest is in Canada. It's called Snow Lab, and it's 2,000 meters because you go through a shaft. It's a mine. And this is important about underground labs. They are very different in the conditions, not in suppression of radiation, whether you get horizontally or vertically. But in any case, what you're doing, why these labs? Is because you put tierra de por medio, this fantastic expression in Spanish. So that means going to underground lab is to put tierra de por medio. And if you put tierra de por medio, you have fewer muons, fewer radiation. And then in principle, you can just test experiments that you cannot do on surface. And that's the reason why they started. So we are there in the Pyrenees. If you like skiing or coming to the mountains, then this is a nice place to visit us. It has lots of history, the famous international station of Canfranc. Some people here visited, so the place is nice. And it's nice. And in our case, we use that is a double tunnel, historical one, the train tunnel that is abandoned since 1970, and a road tunnel. And in between those tunnels that are separated, they run in parallel more than 8 kilometers. They are separated 100 meters. Then we have a space, 1,600 square meters, which have 800 meters of rock on top. And there are a number of experiments in physics. I will go very fast. This is now 40 years when the pioneers started this laboratory. At the beginning, the laboratory was not so different to the NAPAT tunnel. So there was no train, so they could spend more time and leave the experiments there. But it was just basically tuning for the younger. Tuning was invented long ago. They tuned the most fashionable car at that time. That was the 4L. And then once you tune it, then you can just put a box, you put your experiment, and you go inside the line, and then you have your experiment underground. It was a cheap way to do something. And these are real pioneers. The Ángel Morales and the team, Julio, José Ángel, Rafael, really, they started this story. So very short, because this is an introduction, and this is going to be mostly about biology, but just for you to know, and also it's my task as director of the lab. The major things we do is host experiments. This is, by the way, national infrastructure. It belongs to this group of ICTS, instalaciones científicas y técnicas singulares. So we are not a research lab like CSIC or a university lab, etc. We are an infrastructure to serve the community and the company. So it's not our mission to do science, even that, of course, we develop some scientific projects, but mostly our main mission, our main task is to host experiments and provide the best services. If this is about low background radiation, we have to make sure that we are able to measure it. Because if someone tells you, I need low background radiation, this is a great idea, we really need to measure the materials you are going to use to make sure that they are not contributing to the as background to the signal. So we just, with collaborators from Poland, we help to develop now what is the most sensitive gamma ray detector that we know of. It's able to measure 1 or 2 microbecquerels for the uranium line, for the uranium disintegration per kilogram. So becquerels is disintegration per second. So this means is basically we are able to measure things that are extremely pure, clean, and that you see one event every 10 to the 6 seconds. It's about a month, as clean as like that. So the best copper is that or better. Then we develop common equipment or kind of high sensitivity equipment, but we place it in better conditions and we improve the chemistry, etc., to determine concentrations of substances that at the end, after decay, produce important contaminants in radioactivity. And in our case, we reach ppbs. I'm sure that you know about PPTs, parts per trillion. This is 3 orders of magnitude less amount. So this is 1 in 10 to the 10 to the 15. And then we have 2 experiments I would like to discuss now that are in 2 areas. One is ANAIS. They, in fact, already finished the experiment after 8 years. This is a crystal of sodium iodine. It's a very large crystal, 12.5 kilograms. And then you have many of them. And if you put those crystals and instrument them, it's a crystal, it's transparent. You instrument them with light detectors. When a particle, ionizing particle, passes by, ionizes the crystal scintillates, produce light, and you can identify that particle. Those detectors were set up to try to discover dark matter. They didn't, but they did something very important in science. There was another experiment in Italy, in Gran Sasso, that claimed to have discovered dark matter. It was called Gamma Libra. And we needed another experiment done by a different group in a different lab with the same technique to validate it or refute it. Unfortunately, or fortunately, this is science. They refute the signal, so far we don't know what is dark matter. So Alicia, you have a chance. So, and then next detector, which is a try of one of the most novel technologies to detect something very special that we think was very important at the beginning of the universe in the first part of a second, which is one very rare disintegration. So many nuclei, what they do is they change one neutron by a proton or vice versa, and the leftover energy is just thrown with an electron and a neutrino. And this is called beta decay. And it was the second radioactivity process discovered. But there are some nuclei that they cannot do beta decay because the new nuclei will be with more mass, with more energy, so they stay longer. But at some point, they don't produce that effect, that process, but they produce the double process, so 2 electrons and 2 neutrinos. This is a double beta decay. There are a few nuclei that can do that, and the one that we use is xenon-136. This experiment is trying to demonstrate something that has not yet been observed, which is that sometimes one neutrino meets another neutrino, and they tell each other, look, who are you? And say, I can be matter or antimatter. Where are you? And if one is a matter and the other is antimatter, they will annihilate. That's what they want to discover, that neutrinos, being neutral, are the only neutral fermions that we know. All the other fermions, they have charge, so that means matter and antimatter, they have different electric charge. But neutrino, because they don't have it, and if you have quantum states that are indistinguishable, then you are both states at the same time. That's what we think that happens to neutrinos, and that will be we think very important because that will be one particle that is able to talk to matter and antimatter. And we think, and there are numbers to show that in principle indirectly generate why we are here, why we have more matter here than antimatter. And that's the experiment. The half-life of this process is 10 to the 28 years. So you need tons of material to at least observe one event per year. Remember what I said about the germanium detectors, that we can just measure something in a month? So it means we have to characterize materials in a way that at least makes sure that the experiment is able to measure these very tiny signals. And that's the difficulty, and that's why they come to underground labs. Really, it's scientific questions that we want to address that have to be done by that. And just to finish, then let me just illustrate, which is taking a significant amount of my time, is this extremely big project, this Giganti project. This is a cover that was finished in June last year. From bottom to top is 92 meters. Okay. Wide is more than 70 meters. So this cover now is being, well, it took about 3 years to do this excavation. It is very interesting how this is done. It's probably the largest one in one piece. It has 2 access tunnels, one at the top, one at the bottom. And it's certainly very impressive to be just watching from below or from above. In any case, now there are some refurnishing of the walls, putting some steel to build a steel tank. And inside, we are going to put lots of detectors. Those are the types of detectors that we are going to place. Those are PNTs, photomultipliers tubes. They are the largest that are fabricated, 0.5 meter. But unfortunately, they are in vacuum. Well, no, they must be in vacuum because you have an electric field to amplify the signal. You receive light, and then you have diodes that multiply the electrons generated. So you need to protect these PNTs from themselves because those are bombs. If one breaks, then you have the pressure of water coming very quickly to the vacuum inside. And then the first water parts that reaches the center very quickly notice that someone are coming from all sides pressing them. And if you overpress some system, you create a shock wave. 50 bars in 3 milliseconds. 50 bars is a lot. So you really need to build protectors to make sure that this shock wave is contained and doesn't kill the other PNTs. That was the job, one of the jobs of Spain in this big project. So we designed, validating in the sea, verify that they are not magnetized, etc. By the way, INTA helped us on the part of magnetization. So now we are in fabrication phase. This is being fabricated in Spain and will be sent to Japan, and we will have to install one by one in this huge tank, 20,000 units to start with. And we are with lots of pressure because we have to finalize the project in a year. Everything has to be in Japan, and another year to do the full installation, filling water, and start taking data. And the goal is to discover one other property of neutrinos that is very important, that they have a little asymmetry. Neutrinos and antineutrinos, I said that they may be the same, but they are not exactly the same. There is some imbalance that they create. So they have to be fermions without, they are fermions without charge, that they can be a combination of the 2 states, but this combination has to have some little imbalance, and this is what is going to be measured. And this is one, again, important step in understanding where matter is coming, how matter was formed or dominating at the beginning of the universe. And my last step is, to me, what is going to be the most important future experiment in Canfranc. We don't know what is dark matter, and it's around here, around us. And they are very many more than we. In particular, if they are the actions, they are a lot. The question is that they are very calm and silent, and then they interact very weakly with us, with our matter, with normal matter. And that's why it's so difficult to detect them. And that's why the technology to detect these components is so complicated and requires really go to the quantum limit noise to identify these small signals. First of all, generates from action something that can be read, and then read with some very little noise. But there is a region where we think that this happened. That's my contribution. It's just promote to the ones that can build that they should point here. This is the region where we should find it. And don't look at that people are stupid. It's because it's very difficult to work in this region of frequencies. So I hope that in a few years, then we will have experiments there and they discover what is dark matter. And because we know that it's here, we know it by gravity, but we don't know what it is. We don't know the DNA of these particles. Well, this was the introduction onto the lab. Okay, so now let me go to biology, which is the reason of the topic, and maybe some of you came because of that. Why people started thinking about experiments underground? Well, first of all, it came, of course, with the rise of the underground labs. So that means in the 80s, because of trying to understand unification of theories, it was very important to go for these detectors with very tiny signals, or very small signals. So that means those labs were built. And then other communities found that this could be interesting. So people that were working in radiobiology typically, or in radiation experiments, where in the 80s already most of the science was there and it was technology development. They thought, oh, maybe it's a good opportunity to try to test what happens if we go down in radiation to the environmental and below. What happens to life? What happens to cellular process? Do cells and at the end organisms do better or worse by reducing radioactivity? By increasing it, we know it's almost linear relation between more radiation and cancer risk, for example, etc. But if you go down, this continues going to zero, or at some point there is some worsening, etc. That was the idea of some of the pioneers. There are a few people, but really there was an Italian, Luigi Satan, and his team from Rome, that they were really doing different types of experiments, the same group with different organisms. And there is an accumulation of data. For the ones that work in biology, you know how difficult it is to remove systematics, get clear signals, identify what is the right experiment that really brings to you what is the main thing that is happening. Because everything, of course, is convolved in this complex network of things going on. But let me just summarize two statements that I think that comes from the consensus. Also, I must say, sorry that I forgot, most of the experiments come from Gran Sasso, which has horizontal axis, and some other experiments that come with YPP. This is a waste storage underground, so you have to go vertical. So it's not very easy to compare surface and underground. So you have to do experiments both underground. So sometimes even comparing among labs, you have to be very careful. That introduces maybe some systematics, so it's not easy to draw strong conclusions. But based on this accumulation for 2-3 decades, for a community that is relatively small and silent, but there are lots of references that point that there is an impact when you reduce radiation below background, the background that we have here. By the way, I didn't say that. But sorry. This is the radiation that you may take by when you have some radio signal, etc. They want to see to you, or this is for the largest that you can take allowed for 1 year, for example, for someone that goes to the space station. If they stay there for a month or so, this is the maximum, in fact, they can reach. So those are the numbers. Sieverts here is joules per kilogram in damage to your system. Okay, so there are impacts on growth and development. Because I'm going to talk about experiments in the underground lab. That's the main message that I tell to colleagues from biology when they come to an underground lab. All the expertise that you have in your system, that you have been working for years, when you bring and you do these experiments underground, there are things that are going to change. The timing is not the same, things go differently, etc., etc. So there's a clear impact on how life is ongoing, and this has impact on growth, laying, fertility, etc., etc. There's an obvious impact on that. It's one stress, and many of you, or the ones that have been working on many other stresses. This is one more, abiotic. It has before in the past it was normally not considered. But at the end, radiation we don't see with our eyes, or we don't feel it so easily. But yeah, if you remove radiation, there is some impact. And the other is at the level of cells or cellular impact. And there are two effects that I mentioned. What I'm doing now is what I did 6-7 years ago. I tried to sell this story to colleagues just to find some ones that are sufficiently brave to come. And one is there is a consensus that there is an increase of ROS, of oxidative stress, because of this abiotic stress. And second, there is if you just damage the system and see how the repair mechanisms start working, underground, they do worse. Those are the two kind of statements. With that story, I try to convince some people. First of all, I have to convince the bosses of the lab, so that means the ministry and the government, and just to provide some budget. And that's what the first thing we did. Then I told this story. Basically, I told the story as a physicist and a chemist. If a muon passes by, very fastly ionizes in the environment. Ionizes, depending on the energy, larger or shorter. Remember, ionization is no more than extracting electrons from a system. So when this particle passes very fast, then it takes out electrons from some of the molecules there. And this is, by the way, democratic. The muon doesn't care which is the molecule. And as I said, the impact can be larger or in distance or not. But then the second step, it comes chemistry or biochemistry. So those cells, those molecules, they now are talking to each other. These processes also are, of course, slower, but relatively fast. And then different molecules talk to each other and say, look, I lost one electron. I don't know what happened. Something suddenly just took me an electron. I take yours because you have a smaller electrochemical potential. I take yours, and the problem is yours, right? And what happens is that with this effect is all this kind of democratic impact of the passage of a muon is just going into some specific molecules, the ones that have the weakest potential, which in biochemistry is well known that they are the ones that share energy, etc. So they are important. What happens is that this effect that we have been trained for 1 million years or so ourselves, when we go underground, doesn't happen. So all the mechanisms that you have there just to control all this oxidative impact of the passage of a muon, now here your cell notices that I'm doing something, but I don't know why. Yes, I'm trained to do this, but I don't have these passages of the muons. That's somewhat what we think that happens. And with this story, then we were allowed to build 2 biology labs. Someone would say more on microbiology, but basic labs, real labs. By the way, it's the first place in the world that has biology labs, not some small container that you can work there. So, and you can do experiments there. And that's the novelty that I did. So if I did something, is the following. First of all, build this story, and yes, innovate on. We didn't want to do the same that in other labs. One group for 20 years studying different organisms. This is like when you ask for computing time or when you ask for telescope time. This is open to the community, and the community will bring, as you will see, many more ideas that I will never have thought of. So that means this is just open to the community. If you think that this is useful to any of your projects, then we are happy to collaborate and provide some local support. We have some personnel that we hire and also some toolings. We cannot give you money for your experiment, but we can support in a significant way your experiment. So it works like in computer time or telescope time, open calls, etc., etc. We were, my voice is stored, but okay. We were at the very beginning trying to promote and bringing people and so that means now the bosses told us that we have to be more in a regulated way, etc., etc. And that's what we are doing now. So please go to this proposal and read it if you are interested. There are many experiments. In fact, the pioneers are here, that they came with a project on life in heavy water. But I will discuss now more about the biology. So I will not discuss that project. I will discuss projects that are already, in fact, finished or completed. And I will divide in 2 blocks of 3 experiments. That will be my next 5+5 experiments. So transparent slides. One is about specific questions that are very easy to understand the questions. Then maybe getting answers is not so easy, but at least the questions can be understood by someone like me. I'm not a professional in biology. I have lots of curiosity, but of course I am not the expert. But to me, it's very important. If I understand the question, I can sell your project inside. And then this another three, which is the idea that I'm now trying to push. So let me go to the first part. And this is a very interesting and simple question to answer. Well, one fundamental question in the history of life is to understand how was in detail, specifically, the process from unicellular to multicellular. And then there are two lines of work, is taking multicellular organisms and try to get the simplest and go to the simplest ancestor, or go to unicellular that they look somewhat more and more pluricellular. This is the line followed by one of our experts in Spain, maybe some of you know, Iñaki Ruiz-Trillo. And in fact, in the meantime of developing this project, he got an ERC grant to continue his effort. He studies a few organisms, but also he brought a very interesting idea to me, is that, look, what has been done in underground labs, when you think about eukaryotic lineages, is really very few. We are just only testing a few clades in the large amount that they are. So they brought one of their organisms that, remember, they are unicellular, but in some phases on the development, they look like they aggregate, etc., and they have kind of this transition. And the question that they are asking, and then we are supporting this project, is that maybe the emergence from subterranean to a surface and the increase of radiation maybe was a reason just to get together and go from unicellular to multicellular. It's a hypothesis, which at least now you can test. And this is what they are doing, and this is a very interesting project that is ongoing, and in fact, it became a collaboration between some scientists in Canfranc and in the lab. So this is another project. This is I said it before. It led by Menendez from IDG, from this center in Girona, and he works in senescence, cancer, and also aging by the changing methylation, right? So tracking. So, but the question is the following: what they are trying to understand is this induction to senescence, because then here you have again a stress, reduce or impair impact on the reparation. Whether if you damage with different agents, if you see some impact in senescence. And the answer, because this work has already been finished and they are now they already send it to journal, etc. What they find is that if the damage is not severe, they see a significant difference between surface and underground. And now how to model that and how to understand that will come in future experiments, but at least this pilot shows that the induction to senescence is going to be different if there is a variation in the level of radiation. And now they are analyzing the data that they also took. If you affect DNA reparation, you are affecting methylation. And as you know, in the last decade or so, there has been a connection between how the methylation evolves with aging. So they are also trying to understand if this could have some impact on aging of cells. So this is the second project I wanted to say that those are research groups that they come with their project, is presented, is evaluated by a panel, is approved by the lab, and the lab provides support. So it's not LSC research, it's the scientists that come to use the lab for testing their ideas. And this is the third and very curious result. I hope that you appreciate that whether this is true or not, that the question is very interesting and well posed. This is particularly when you think about biology and all the complexity. If it is true that there is some impact on these reactive oxidative species, so that means that you are impacting on oxidative processes, you could take one of these oxidative processes that happens in cells, just, in fact, take it out from cells, do it in vitro, take one of these kits that does this reaction, and verify if the chemistry knows whether it is underground or on surface. Whether this is just a pure chemical process, in the sense the state of passages of radiation impacts on the state of oxidation and therefore impacts on the velocity or the speed at which this process happens. That means at which process you are repairing oxidative or controlling oxidative species or not. It's not just a pure chemical reaction. There is lots of control in what is happening at the biological level. That's the question that is time to be addressed. And we have the first results. Now this is now being studied and validated. The reaction, as I said, is very well known. Then you have some oxidative component. Then you have the glutathione with some enzyme. And then what you control is the absorbance of NAD in this process when you change from the oxidative to the reduced component. And our first preliminary results seem to show that there is a little variation. Seems to show that the reactions may be slow. This will be completely new and novel, but still it's very preliminary. So we have to really repeat the experiments, control all systematics, because this will be a very bold statement. So we have to make sure whether this is real or not. In any case, just learning if it is the same or not is a very important message, whether it's pure chemistry or it's really biology control at the level of genetic, the microRNAs or whatever other types of components. This was the part of which experiments are going on. There are more. So the ones that need more information, go to the webpage or ask us or bring your ideas. If in your processes, ROS, DNA reparation is important, maybe this is an abiotic stress that may be important. So now let me go to the last part, another 5 slides, and then I have these 5 minutes. And also this comes from some experiments. Well, one of the teams that, and this is not only this team in Spain, they have been others. They have been also working, I think also it was a project at the European level. They just participate in some project of trying to understand the stress generated by different agents, but in particular gravity. So you can buy some, for small masses, tools to mimic a reduction of gravity on average. So it means you can test lack of gravity now in your lab with a reasonable, affordable cost. And then on average, you are just having some fraction of G, which can mimic gravity in planets, but also a small one at the level of, I think the smallest is 1%, within an affordable cost. This is what we bought in the lab. And this was because it was required by, well, this was at least discussed with one group that wanted to use the underground lab to test also not only this level of this stress, but also the lack of the reduction in radiation. Why we can buy that type of equipment? Because it's useful for more experiments. In fact, this opened an area for us. So that means we did that in agreement with Santiago Elena, that he proposed this project with his team. And they have studied, and this is already documents that are published, or at least are public in the bioarchive. I will not get too much into the details, but they observe, and this is the main message, yes, of course, there is some stress known that has impact at the cellular level, but also at the organism level, because if you change gravity, your membranes are affected, and then viral infection, which is what they study here, of course, is going to be different because depending on the membrane, it's going from one part to the other, so it has to travel cell to cell. So there is an impact, certainly, and how the stress that generates the viral infection, but also the stress that generates the lack of gravity. And then also they found that the lack of radiation also gets some stress. And sometimes, and this is what they discovered, in fact, in this case, they don't go in the same direction. So different stresses, they may not be adding, they may be even compensating. And this is what they found partially here. And then they study what they think, and they can find at the transcriptomic level what things are under or overexpressed. And again, this is their expertise. I will not get into that, but this is another example how infection may be affected. And this is an important, very practical question. So if you send people and they are under these abiotic stresses, you need to know what will happen with their health status, etc. So it's and this is one. And I'm only mentioning, of course, because it was in the lab. But this is what is very useful to have one infrastructure that hosts ideas from you, from the community. because then from ideas of some group, then you build even bigger or bold ideas. So once we got this equipment, my job is making sure that I do the most that we can in the underground lab with this equipment. So I start thinking, oh, wow, this is reduction of gravity. And in fact, I remember one referee told me in one short document I wrote saying, oh, it's very interesting to have lack of gravity underground because at least you are isolating phenomena. Because when you do lack of gravity on surface, you have lack of gravity with radiation. Now you are just lack of gravity, no radiation. So it's good, this comparison. So very interesting that you have this talent. Okay, look forward to see more results. But I thought, what other stress you have in space or in general differently to being on the surface? And I'm counting the three most important, I find. And I think this is the order in importance. The first one is very well known and widely studied. And recently, in the last few years, it has been shown that probably was overlooked. And this is more problematic than was thought 20 or 30 years ago. So it means after revisiting, then the importance of radiation in space is more than initially anticipated in both calculations, etc. But there are many or a variation of types of radiation that you receive when you are in space. One is the general one, which is the galactic cosmic rays, is the ones that produce muons and neutrinos here on surface, which is the main radiation we receive, muons. But those one is the one that has been produced by explosions of all stars, but all the astrophysics problems, etc. And then it's a constant or and well-known component, 90% protons, about 8% helium, and then others, with energies peaking 3-4 giga-electron volts, very energetic. So at the very beginning, they ionize, and afterwards, they do more things. And yeah, that means this is has a very big impact in the sense of energy. And then when they collide to the shuttle, they produce lots of neutrons, etc., etc. But this is low flux, it's few per centimeter squared per second. Then there is another one that is also widely known, and I think here is one center that I'm sure that there are many people experts on this, which is when you have a solar flare or some big coronal ejection, where you have more intense flux, but energy is lower. Typically, it's hundreds of MeVs, 400, 500 is the peak, and then but the flux is 10 to the 7, 10 to the 8, and during some period of time, we can go from minus 2 hours. Then you have a really big radiation. And then there are others when you are in lower orbits. This is one of the stress. The other, I said it, gravity, because we travel through orbits. And the third one is lack of radiation. And then once you see this picture, the thing is how well we can do beyond going to space. Well, one thing is we go to space and we test the three at the same time, because in space there are no muons, because there is no atmosphere to have the collision between protons that come from cosmic or other cosmic rays to nitrogen and oxygen that produce the decays, and because there is atmosphere, there are pions that decays to muons. In space, that doesn't happen, so there is only the primaries and lack of radiation. So that means you don't have that we have on surface. So my question was, because I have the responsibility to be an underground lab, is how this may impact the results that we already got in these areas, without going outside, because as you know, it's more expensive and you cannot do so many experiments. So, and this is, there is an expression for that, but this is the cheap way to see that. So remember, this is what you need. Let's make it cheap. We have an accelerator. For example, here in Madrid, you have an accelerator that you can go to 10 MeVs. We have now machines that you can go to 400 or several hundred, the proton therapy machines, and you can go to GeVs if you want to CERN. So in principle, we have machines that can mimic all these contributions from radiation on surface. So we can do that in principle. Then we may have tools that mimic the lack of gravity. And to mimic the lack of muons like in space, you have to go underground. So with these three elements, we are trying to do something. The very first thing is we got a proposal, which is maybe for the people, for me, this was completely new. In fact, it's the most fascinating thing about the biology platform is how many different projects and ideas we have in the community. This is a project to show what happens in the first stages of development of fishes, with the goal, maybe in the future, to bring some fish factory, I don't know, to Mars or etc. So that means that you can eat fish and not some powder. And the very first thing that they did is test what happens to this development without gravity or with reduced gravity with this machine, and also with reduced background radiation. Of course, they find if you saw at the very beginning there is impact on growth, on fertility, etc. They already said changes in the stage of evolution of this development. And in fact, thanks to these first results, they got an approved project, this project's program that maybe is known here because some of you probably applied to this. So just to do the similar experiment in this International Space Station. So our lab served at least to show that this is an interesting project to do. But now let me tell you, just to finalize, and this is reasonably within time, is what we are doing, developing a technology not as an experiment for the lab, but as a kind of protocol for the ones that may need it. As I told you, if you want to test what happens in space, the most expensive but maybe best realistic, go to space. But this is very expensive and takes lots of time. If you want to do something fast and within at least before I retire, then we are going to, or we are trying to provide some organized program. So we have this tool that if it is needed, we could just invest and grow, because always it's cheaper for a community if it is in one lab and then it's used for the community. So we may even increase it for larger samples just to have microgravity. And then what we do, because there is in any of the labs in the world, we don't have an accelerator as we need underground. So formally, we cannot do the experiment. So what we do is what was cheap to do in physics experiments 50 years ago. So we do the biology experiments and then quickly, I am the driver. So you go to the accelerator, irradiate, and bring your samples back to the stage where they have been 1 month underground. With that, of course, you are, having some impact. The trip may have some little impact, etc. But at least this is very reasonably cheap just to demonstrate whether this is valid or not. And then we are testing with, as I said, tens of MeVs, hundreds of MeVs, and GeVs to show these three effects combined and separated. I will not go into the preliminary results. Before that, I'm going just to read take-home messages. European underground labs are national infrastructures ready to host your experiment. And then our plan is to explore life in low background radiation. This was the initial motivation. Second is isolate microgravity from radiation. And third, in combination with a proton beam facility, then explore the three abiotic stresses, separated and combined. But this is, I don't think, the last step of this story. But if this story is successful, certainly it will promote, it's not so expensive, and then we have the technology to do that, just to really build a European lab underground. It doesn't have to be tremendously deep, but that contains an accelerator, that contains an ESA facility to also do microgravity, where you really can do these long-term experiments. For example, a trip to Mars. So you can put your samples there, and then you can do all this preparatory phase in this as similar conditions as possible. And this is what I'm after. And anyone is welcome to help and support. And if interested, again, check and come and visit us in Canfranc. And I think as my time is over, I'm ready to questions or comments. Thank you.
Hola. Thank you very much for the great presentation. So is there any question here?
If you don't ask questions, I tell you other stories. Well, I just passed by, but for the first time, there is one experiment from someone here in the CAP. I think you are still formally in CAP or no? Yeah, that is going to come soon, a new one. And then there is one that were the pioneers. The pioneers also are here. Those were the first ones that came to Canfranc with a project on life in heavy water. This is, and they also host this record. They are platform biology 0122. So and then this program, I didn't say it, by the way, it was approved for 10 years. So we got a grant, which is not exactly a normal grant, but okay, it's just to make sure that we explore the most how this infrastructure can help the community.
So I have a question about related with most with the financial thing about the function of this laboratory. So there's any charge for scientifics if they want to send you any samples, or there's a possibility to have an agreement between institutions to carry on these experiments in this laboratory?
Yeah, this is, thank you. This is a good question, because this is one of the first difficulties that find in physics, and in this particular area that is astroparticle. So we are very used to use infrastructures outside. So that means in most of the national programs, etc., it is included a part for that. So it is already well understood by the managers of the budget, etc., that there should be some part of the budget for trips, hostage, etc., etc. That doesn't happen in biology. Still, that culture we were not able to cross. Maybe in some specific groups that come to some of these European facilities, but it's not common. So normally you don't have in your budget that type of payment. But okay, so I understand that very well, and this is an issue, in fact, and it's a big difficulty. And if you talk to some of the experiments there, that's for them a difficulty, because it costs some money going there or staying there during the experiment. And this is against the other thing, is that the money we use, it doesn't come from a competitive project. It's money that the government or the managers of the lab, the owners, then give up to us. So because it doesn't go through a competitive program, I cannot give money to you. I can buy equipment that is of general purpose. So it means we can support, we can invite someone because it's providing training our team in something, but we cannot pay your experiment in that sense. That's you see so we try to do our best. So we have some team of biologists, but we started with one, which is I would say a high-level technician, which is fantastic. That is the one that just build the lab and provide support. So that means kind of, as you know, in many biological experiments, there are many things that you have to do like a routine. We can do that for you. But of course, you have to come at the beginning, and also you have to do some work there. So some work from your side is needed, but kind of regular activities that doesn't require full weeks in many months, then we can provide some local support because we have personnel from the biology platform. So we try to accommodate too, and hopefully in the future this will be included in the programs, and you will really get budget to do the experiment how you want. At this point, you really have to collaborate with us. And the collaboration can be just technical, we provide support and minimal, or can be deeper depending on the needs.
Thank you.
More questions?
So thank you so much, Carlos, for showing us our initiative that is proven to be of interest of CAF, because we have two colleagues that are actively working with you. But I'm wondering, in this facility, one of the things that you highlight is the shielding properties that you have in there, that you are sealed from the radiation, but also being underground. I think it's very important that you have very stable conditions, that you are also sealed for a long time from circadian cycles and other kind of stuff. On the way that you are focusing the experiments there, what is the time frame, the maximum time frame that you are working with? Because I wonder if you can do some long-term, experiment to have, I don't know, some organism or some kind of, even for materials or something, to have there in a long time to be, sealed for a long time.
Yeah. Long time is very problematic in biology. Long time is very easy in physics projects. we are used to very long time projects. But in biology, it's very difficult because even organisms evolve, right? So that means how are you sure that what you have after 3 years is exactly the same? So you really, but it's a part of the project. But your point is right. This platform at least has been approved for a decade, and now we have been running for now 4 years. So that means it's still 6 years to go. None of the projects is still long term, but certainly we have been talking, and I think other labs. Of course, when you are underground labs and then they are telling the world, you know what others do. And then we are, of course, collaborating and competing. This is science. So that means they are, of course, looking how successful it is. The success of this biology platform so far is that there are many different projects running at the same time by different experts. I think this is the great success. I just can go home and I got my salary well paid because that was a success. What is the science coming from there? We will see how much we can learn. There's no magic, so things are step by step. But other underground labs now, we started creating a network, and then there are some projects that we want to do in different underground labs, the same type of experiment and also long-term experiments. And there are a few, and we are starting on that because also different underground labs, they have different conditions, and then at least we want to understand which of them, because at the end, different underground labs is like testing different levels of radiation, testing different levels of other parameters that may influence. But just because you ask about that, then there is one project in France, for example, in the Modam lab, which is the following. One of the things that is done in medicine is to have these stem cells, which are very useful, etc. And the question is, how sure I am that the stem cells are not affected by radiation? So what they are studying is stem cells long-term variation underground. So they are maintaining, I don't know what temperature, probably liquid nitrogen or whatever. But now is what is their stability as stem cells along many, many years, and comparing outside and underground. So there are this kind. So when there is a good physical or practical motivation, there is natural to study this. And then the other that, for example, the one that we are doing underground labs is take something that you lyophilize, right? That in principle you say, it stays there and doesn't happen anything to them. So we want to verify up to how far this is still valid or has been affected or not. So there are maybe some of these long-term projects, but maybe useful as somewhat what you assume as a standard that they are stable, maintained, etc. Whether this is true or not, and then whether radiation may be damaged, etc. So that means we are touching this kind of long-term projects. Which, they has to be very specific, at least to get some utility. They are not very cost in the sense they take some little space, you maintain maybe some temperatures, but of course, but you have to live and stay and maintain and make sure that nobody just turns off the machine.
Thank you.
Are there some questions online?
Yes, from Zoom, from the director, Victor Parro, is asking, do you have facilities or plan to have for simulating the effect of no radiation on humans? I'm thinking of astronauts for spending significant time in the facilities. And related to this, how compares the difference in radiation doses between underground facilities and surface with respect to the difference between surface and space station?
Okay, many questions, Victor. Thank you. Okay, so let me see if I remember. There are, at least I separated, I think, 3 questions. So let me see if I answer to all of them. So first of all, experiments on humans, not so easy, but certainly in underground labs, we are talking about to get the closer to humans that we can do. And one of the things that we are really discussing is if we can go to experiments on mice. This never has been done. Physicists are scared about mice, not me, but I have to live with my community. They think that mice are going, I don't know, eat some electronic car. It's well, in any case, but the thing is, one thing is very relevant with respect to that this we know with respect to underground labs. So what is important here is the cell cycle. If the cell cycle is short, your experiments, so that means you get somewhat, the word is you notice this difference being on surface and underground after a number of cell cycles that, for example, for some organisms, may be a few days or so. If your cell cycle is much, much longer, then your effects of being underground are longer, so your experiments get really long. So you really have to plan. But so far, they're having no experiments on humans for this part of the lack of radiation, just answering to that. But I hope that this will happen. And I think I think that at some point will happen. By the way, we got someone that called us saying that this person offer himself or say that he would like to spend 1 year underground and see the biological effects. That will be, by the way, very automated. So this kind of experiments have to be planned very well. This was question 1. So the second, if I remember correctly, was about radiation, how much it compares. In our case, the flux gets reduced in 10 to the 5 in the number of muons. So if I look at these numbers, so the thing, I try to say it at the end. The lack of muons generates one effect. The protons that we get in the space is another effect. But because I have this question, so this is the amount that you should at least get in space in a typical 1 month stay in the International Space Station, I think. About factor 100 less is what you have, well, maybe factor 50 or so, but okay, factor 100, I will say just orders of magnitude, is what you have in surface. And underground, we have another 1-2 orders of magnitude less. So in orders of magnitude C, in biological impact, although this is millisieverts, you are so low that the thing is, you have different effects. In the case of larger radiation, you really go to damage. You get these cancer rates. You really get lots of breakings, double DNA breaks, etc. So you have many things. Here, it's not that you impact directly on the DNA. You impact on probably regulators or chemistry that impacts on the DNA. So that's why biologically they are different. But yeah, for the numbers 100.1 and 101, 10 to minus 2. And there was a third question, but now I forgot. Is okay? I answer?
Yeah, this too.
Okay. But if someone brings or thinks about experiments, I would like to push, I know it's difficult and it takes money, time, and effort, to have something similar to experiments, because that will be the most realistic thing for before going into humans. And I know that there are many issues, but in principle, this is done on surface. So I don't think that mice will be worse on surface and underground for this experiment. So, but yeah, it will need time and regulations.
Okay, so I think this is all. I encourage you to visit the lab and send your proposals.
Thank you.
For the experiments. And thank you, Carlos, a lot for being here.
Thank you for joining. Yo creo, tú estás